Alright guys, I think for the rest of our problems today, we'll just do the FRQs for the remainder of today. If you already did some other ones today, I'm going to be requiring you guys to do numbers 1 through 4, and then the FRQ questions. And that's a total of 5 for FRQs. So it's a total of 9 questions I want you guys to complete. So if you've already done 9 questions, it doesn't matter to me if you do the FRQs or something different. Just as long as you had 9 for the day, I'll be good enough. There's a lot of repetition in here today, and these problems are taking us a while to complete, and so I think we can go ahead and scale back a little bit for today. All right, so let's begin here. This is the first FRQ question. It says, let f be the function defined by this piecewise function here. And so this curve up here is the piecewise function. R is the region in the first quadrant bounded by the graph of f and the x and y axis. So here's the function. Here's the x-axis, and here's the, wow, having trouble writing today. Here's the y-axis. And so the area between those lines is the region R. All right. Let's see. So they want us to find the area of R. All right. So to find the area, basically we're going to find the area between this curve and this curve, and that'll find us that area starting from this boundary point and ending at this boundary point. And so that's going to be the integral from 0 to 2 of our function minus 0. Now we don't really need the minus 0, so I think I'll leave that off. Now this is a piecewise function, and when you have a piecewise function, you've got to break it up into your pieces. So how will we do this? Well, it looks like my function from 0 to 1 is this function, and then from 1 to 2, it's this function. Now my integral goes from 0 to 2, so I'm going to have to split this thing up into 2 separate integrals. From 0 to 1, it's this function, and then from 1 to 2, it's the other one. All right, now this is something we're going to have to do by hand. This is not a calculator question. So first of all, I'm going to go ahead and FOIL this out. X minus 2 squared. What that means is we have x minus 2 times x minus 2, which is x squared minus 4x plus 4. You actually, I think this one also could have been done with u substitution. It might have even been easier doing that. I'm just going to stick with the strategy I've chosen here, but there's that. All right, next we're going to integrate. So if I integrate this first one here, I'm going to get 2x plus x cubed over 3. Actually, it's minus x cubed over 3. The next one, we integrate that. That's going to be x cubed over 3 minus 2x squared plus 4x. And that's from 1 to 2. And then we're just going to apply the fundamental theorem of calculus to both of these. So I'll plug in 1. Oops. 3. Then we'll also plug in 0. Now when I plug 0 in here, the whole thing just becomes 0, so I'll just put a 0 there. And this is going to simplify to 2 minus 1/3. There's all that. Let's go ahead and do the next one here. This one's going to be kind of messy, so we better make some space for it. All right, let's plug in 2. If I plug in 2 here, I get 2 cubed over 3, which is 8/3. Plug 2 in here, I'm going to get -8. Plug 2 in here, I get +8. And so those cancel. Then we'll also plug in 1. Plugging 1 in here, I get 1/3. 1 here, I get -2. And 1 here, I get 4. So we've got 8 over 3 minus 1/3 plus 2 minus 4, because I distribute the negative, right? Changes all those signs, right? Let's see. So I've got, let's combine the thirds. I've got a -3rd, a -3rd, and an 8/3. That leaves me with 6/3, and 6/3 is simply equal to 2. Then we have 2, 2, and -4. All of those cancel each other out, and it looks like I'm left with just 2 there as my answer. So that would seem to be the answer there for part A. All right, moving along. All right, so for part B, R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. So perpendicular to the x-axis means we're doing dx. The fact that we're doing cross-sections with a square means it's going to be the base squared. And the base is the distance of your function to the x-axis, which once again is really just the function. Okay, and we're going from 0 to 2 still. It's still the same region there. Now, once again, because it's a piecewise, though, we're going to have to split it up. We're going from 0 to 1, and that is 2 minus x squared. And then for the second piece, from 1 to 2, we're doing x minus 1 squared. And in this case, we have to square our bases. Okay, and that's as far as we really need to go with it. It's just we had to split this function up into 2 pieces. From 0 to 1, it's this, and from 1 to 2, it's this. But that would be it. They didn't want us to evaluate it. They just want us to write out the possibility. All right, guys, for part C, it says the portion of the region R for 1 to 2, so we're only going to be looking at this piece here, is revolved about the y-axis. So we're doing a revolution about the y-axis, which means that it's dy, and we're integrating from 0 to 2 up vertically now. And it's going to be pi times the radius squared. And the radius is really just going to be the distance of our function to the y-axis. Now, to do that, though, we need to get our function in terms of y. So, right now, we have y equals x minus 2 squared. So to get this in terms of the correct variable, we're going to square root both sides. And then we're going to add 2. And that would be my radius. Okay, and from there we're supposed to do this by hand once again. So the first thing I'm going to need to do is I'm going to need to square this thing. Multiplying those, I get y. Multiplying square root of y times 2, I get 2 radical y. Another 2 radical y. And then a 4. So altogether we have the integral of y plus 4 square root of y plus 4. Now I'm going to rewrite this square root here. I'm going to change that into a half power. And let's get to integrating. So if I integrate y, I get y squared over 2. If I integrate 4y to the half, I'm going to have y to the 3 halves. And then I'm going to divide by that number. And then integrating 4, we have 4y. Now I'm going to simplify this one in the middle here. Instead of dividing by 3 halves, I'm going to multiply by the reciprocal, which is going to result in 8 over 3 instead. There we go. And we're plugging in 0 and 2. Now since this is an FRQ, I would probably just plug in the 2. I get 4 over 2 is 2, plus 8 times 2 to the 3 halves. I'm not going to simplify that. I'm just going to leave it. And then plugging in 2 here, I get 8. And then plugging in 0 would be kind of pointless because it's just going to all be 0. And I'm going to leave my answer like that because it's an FRQ and I don't have to simplify with FRQs. Okay? So that'll be it for part C there. All right, guys. I'm going to do another one of these things. This one's not too horribly different. We do have to do it by hand, and I think the one part that you'll probably want help with is doing the integral by hand part. The setup, though, is pretty much the same. For part A, we want to find the area of region R here. So to find the area of a region, you do the top function minus the bottom function. The top function is this. The bottom function is the x-axis, which is 0. So really, to find the area, we're just going to integrate this from 1 to 4. All right? Do that. Okay. So now the problem that we're going to run into is in rewriting this expression here so that we can actually integrate it. So it's what it is. It's kind of like a really messy looking split the numerator type of question. I'll show you what I mean. So the first thing I'm going to do is I'm going to distribute this 3 in. Or we could honestly just take the 3 out. I think that would work also. Why don't we do that? Let's just take the 3 out of the brackets like this. Why not? It's just a constant multiple, and you're allowed to take out constant multiples. Okay, next thing I would do is I would split the numerator. So I would have x over the square root of x minus 1 over the square root of x. The next thing I would do is I would rewrite the square root as a half power. And then the next thing I would do is I'd simplify each one of those a little bit. X over x to the half. Well, whenever you divide x's, what you do is you would subtract their exponents. So 1 minus a half is a half. So that just becomes x to the half. And for this guy here, I'm going to move it up to the numerator and make it negative half. All right. So that's the trick there. I think after this, you're not going to be too surprised with most of what you would see on how to solve this. Just getting that thing to be rewritten, though, was probably the biggest part. So let me clean up my space here and we'll finish up the problem. All right. So integrating that then, if I add 1 to this, I get, or add 1 to the power, I should say, I get x to the 3/2. And then we divide by 3/2. But I don't like dividing by fractions, so I multiply by the reciprocal. Minus, next one, add 1 to the power, and you get x to the 1/2. And instead of dividing by 1/2, I'm going to multiply by the reciprocal, which is 2. And we are going from 1 to 4. All right, so we've integrated. Let's go ahead and plug in. All right, and since this is an FRQ, that's where I would stop because we don't have to simplify that. But I would like to show you guys how to do something here, just in case you have a multiple choice question that involves stuff like this. How would you do 4 to the 3/2 power? That's the only part I think you guys might struggle with there. So how would you do that? Well, think of it as a root. It's a square root of 4 being cubed. So it's 2 cubed, which is 8. Okay? But the rest of it, I mean, we could do the work, but there's really no point because it's an FRQ. So we'll go ahead and just skip it from there. All right, let's go ahead and move on to our last bit for the day here. So we're doing a volume of revolution here. We're going around the x-axis, so that means it's going to be pi r squared, and around an x-axis means it's a dx problem. Anytime you have a horizontal axis, it's with respect to x, which means that our limits are going to be the same thing they were before, the x values of the beginning and end, which are 1 and 4. The radius is going to be the distance from the curve to the x-axis, which is just that function itself. So we have 3 times x minus 1 over the square root of x. So there's our setup for finding a volume of revolution. The only downside is we have to actually do this now and simplify it by hand. So let's go ahead and get started. So if I were to square the 3, I would get 9. If I were to square the x minus 1, I would get x squared minus 2x plus 1. And if I were to square the bottom, I would just get x. Now, some of you guys might be wondering, Mr. Bailey, where did the x squared minus 2x plus 1 come from? Well, x minus 1 squared, that means x minus 1 times x minus 1. And you would have to FOIL that out. And if you FOIL it out, you would get this trinomial. Okay? I'm going to go ahead and distribute the 9 in here. And I'm going to split the numerator. So I've got 9x squared over x. And then I've got 18x over x. And then I've got 9 over x. And we can go ahead and simplify that a little bit to be 9x minus 18 plus 9 over x. All right, now we can go ahead and integrate. To integrate the 9x, we get 9x squared over 2. To integrate the 18, we get 18x. That guy is going to be an ln problem, but it has the 9 in the front, so that's 9 ln of the absolute value of x. And then we're ready to go ahead and plug in and solve. So we have pi, and plugging in our numbers, we get 9 times 4 squared over 2 minus 18 times 4 plus 9 times ln of 4 minus, and then we plug in the 1. And I don't have to simplify this because this is an FRQ, and I am done. All right, so that would be it. All right, guys. I think we'll call it quits there. Hopefully it was helpful, and we'll see you guys tomorrow. Have a good one.